Hello everyone, I'd like to talk a little bit about balancing chemical equations, and I want to give you some additional methods to handle this. First of all, there is the understanding of what a chemical equation is. Let's start with one that you should be familiar with, the formation of water. That is the use of hydrogen gas when it reacts with oxygen gas can form a molecule of water, which is typically in a liquid form at room temperature. Now, this is a representation of a chemical reaction, but at this point it is not correctly balanced. As you can see, there are two hydrogens here. Of course, there are two hydrogens here. There are two oxygens here, but there's only one oxygen atom here. So consequently, it's not correctly balanced. What we want to do is put together a system that organizes this so that the same number of atoms occur on the left-hand side of the arrow as occur on the right-hand side of the yields arrow. So in doing so, what we want to do is have a systematic approach to this. And one approach is to apply a simple back and forth addition and do a visual inspection, for example. We could take a look at this and say, well, there is one molecule of water here. We could represent it, for example, by saying, well, here's an oxygen atom and it has two hydrogens. Over here there's two oxygen atoms. Over here there's two hydrogen atoms. And we can see, well, in order to make things fit, if we had more of these water molecules over here, okay, then we'd have two oxygen atoms. Well, that would take care of this part. And we only have two hydrogen atoms here, and we have four of them over here. Well, if we had another set, we could do this. And by simply writing this back and forth in this fashion, we could eventually balance the equation. However, it might be somewhat tedious to do so, and there's some approaches that you can use, some described in your text and in other videos. So I want to go through this again with you to process an approach that you can use as a step-by-step. So in this case, what we have is a molecule of hydrogen, which consists of two hydrogen atoms, a molecule of oxygen, which consists of two oxygen atoms, and a molecule of water, which consists, of course, of two hydrogen atoms and one oxygen atom. So in order to begin the approach here of balancing it, we might start with this concept of saying, let's pick something that contains the most variation in the total number of different types of atoms, or, if you will, one of the more complex parts in this. One of the more complex parts is certainly the water. Here it is, H2O. Now, what we can do is we can write a coefficient, and this coefficient means how many of this whole package are available. If we pick the most complex one here in terms of water, we might say, okay, there's one molecule or 1 mole of water here, and we'll just write that in for now and just say that we have a set here that represents the part that may be partially completed. So we have step one would be to write the unbalanced equation. Okay, and step two would be to place a coefficient of 1 in the most complex molecule. Okay, we've done that. Now, as you can see, the balance now fits for hydrogen but doesn't fit for oxygen. So let's put this for a more detailed step. We could say, well, this is a 1 here, and so now the hydrogen is balanced. However, as mentioned, the oxygen is not balanced. In order to get one oxygen over here and have two oxygens over here, we can use a simple mathematical process, and that is to say we can take this number, which is the subscript, and make sure that we use that as a denominator. And we can take the number that's over here for a subscript, which is implied, and multiply it times this number, the implied number here is 1 multiplied by 1 gives us the number 1 in this case. So we would then say, as the next step, we multiply this by a fraction necessary, so H2 gas. So we take the number 1 and place it as a numerator over the denominator of 2 oxygens. And this gives us a mathematically correct version of this equation. So we have to multiply by the appropriate fractional coefficient. Okay. Well, obviously we can't have half of a molecule of oxygen. So the next thing that we want to do is we want to multiply by the denominator of this whole process. And just like in algebra, whatever you do to one side, you have to do to everything. So in this case, we would multiply by 2. So we would say 2 times the hydrogen, which is now 1. Let me fix that by putting it in the other way. So we'd have 2 times, because that's what we're multiplying it by, times hydrogen, plus 2 times 1/2 times oxygen, yields 2 times 1 times water. And then if we carry out the multiplication, so here we multiply by the denominator. So over here it's obviously 2 hydrogen molecules plus 1 oxygen molecule yield 2 water molecules. And now we have a balanced equation. And understanding that the balanced equation is always going to give you a situation where you have the smallest whole number ratio of any of the parts to each other. So in other words, they have to be whole numbers, and in this case it's a 2, 1, and a 2 as a coefficient. Okay, so let's try another one that is a little bit more complex and see if you can organize this for your process. So let's take an example where we might have a situation where we're dealing with something like ammonia, for example. In making ammonia, we have nitrogen gas plus hydrogen gas. And when these two react under the appropriate catalytic conditions, we have ammonia formed as a gas. Now, obviously, again, here we are, where we have 2 atoms of nitrogen on one side, 1 atom of nitrogen here, 2 atoms of hydrogen here, and 3 atoms of hydrogen here. Obviously, it's not balanced. So if we follow the same procedure, let's just take it step by step. First step is let's organize it so the more complex structure, we put a 1 in front of it. So we have a 1 NH3 as a gas. Okay. So now it's going to look a little funny, but let's put this here for now, and I'm going to walk through it as a step by step. Obviously, we're still not balanced, but we notice that if we have 1 nitrogen over here and 2 nitrogens over here, that means we have to multiply this by a half. So if we say, okay, 1/2 nitrogen gas of N2 plus H2 gas yields 1 NH3 gas. We notice that, okay, the nitrogen is mathematically balanced, but the hydrogen is not mathematically balanced. So let's just do the same thing we did before. Let's take this coefficient this subscript times this coefficient, which is 3 times 1, and put it as a numerator for this. So we now have 1/2 nitrogen, and here's our numerator, 3 halves hydrogen yields 1 ammonia. And if you do this arithmetically, you'll see that everything multiplies out correctly and you have the same number on both sides. However, as we pointed out earlier, you can't have half of a molecule or 3/2 of a molecule, so we have to multiply through by the denominator. In this case, it happens to be just one denominator, that's 2, so we multiply everything through by 2, and say 2 times 1/2 of nitrogen plus 2 times 3/2 of hydrogen yields 2 times 2 times 1 of ammonia, and now doing the multiplication, we have, of course, N2 gas plus 3H2 gas yields 2 NH3 gas, and you'll notice that it's balanced. Again, the same process. So what happens when we have something even more complex? Well, let's do one that's very complex. Let's do something like table sugar, which is sucrose. And sucrose is C12H22O11. And when sucrose is consumed by us, it goes through a series of metabolic steps, which eventually is reacted in a series of steps, but effectively we're burning sucrose. So if we just took sucrose and actually burned it in an oxygen atmosphere, we would get carbon dioxide as a gas plus water. Okay, so this looks kind of complex, but let's just walk the way through like we did the others. Obviously, the most complex one here is sucrose, so let's just take care of that first. Let's put a 1 in front of the sucrose, and then continue. And we have the CO2 as a gas plus the H2O. Now, you notice that one of these contains only one kind of atom, and that's the oxygen gas. The others have more than just one kind of atom in there, so we're going to do that one last. Could do it otherwise, but it makes it even simpler to do it that way. So if we have a 1 in front of this and just fill in the others, so we have a 1C12H22O11 plus oxygen gas. Now, how many carbons? We have 12 carbons, so we're going to say 12 CO2. And how many hydrogens? We have 22 hydrogens, so we're going to say plus 11 H2Os. That gives us the 22. Okay. So now what we want to do is we have a coefficient in front of the sucrose, we have a coefficient in front of the carbon dioxide, and we have a coefficient in front of the water. The only thing we don't have a coefficient in front of is the oxygen. Now, in this respect, we can take a look at this and say, what do we have on the left-hand side and on the right-hand side? And any difference we can make up using this simple approach by looking at the oxygens. How many? We've covered the number of carbons is 12, that fits. The number of hydrogens, 22, that fits. Let's count the number of oxygens over here. Over here we have 11 oxygens. Over here we have 24 oxygens plus 11 oxygens. So over here we haven't counted it, it's empty. So we know that 11 plus something has to equal 24 plus something. And so what we're going to do is we're going to add this up and make sure that we end up with the same. And obviously over here we have a total of 11 plus 24. We have 35. And over here, 11 plus something has to equal 35. Well, the 35, it's 24, right? Well, the 24 means that what we're going to look at is having 24 total oxygens. So in order to get 24 total oxygens, we would need to make sure that we end up with the correct number here. So obviously we need to have a 24 oxygens total in this setup, 24 oxygen atoms. And in order to have 24 oxygen atoms, that means that each molecule supplying us with 2 atoms, very simply put, the coefficient here must be not 24 but 12, right? So the number would be 1C12H22O11 as a solid plus 12 O2s as a gas yields 12 CO2s as a gas plus 11 H2Os as a liquid, and now we have a balanced equation. Let's try one more example, and we'll work through the process here for the setup using one more example of a reaction. In this reaction, we're going to take some zinc compound. In this case, let's take some zinc phosphate. Now, zinc phosphate is this formula. It's somewhat more complex, it's solid. And if we take this zinc phosphate and we react it with another material, let's say we're going to react this with sodium, and by reacting the zinc phosphate with sodium metal, we're going to make sodium phosphate and we're going to end up with sodium phosphate plus zinc metal. Again, we can use the same procedure as we did before. And in this case, if you look at the 4 structures, obviously we have zinc phosphate versus sodium phosphate. Zinc phosphate is somewhat more elaborate, more complex. The other two, of course, being solid sodium and solid zinc, are not anything but elements, so they're fairly straightforward. So if we take the zinc phosphate as the point of start for this reaction, so we put a 1 in front of the zinc phosphate, and that gives us the first step plus the sodium, okay, yields sodium phosphate plus the zinc. Okay, so now we take a look. How many atoms of zinc do we have on this side? We have 3 atoms of zinc on this side, so we're going to put 3 atoms of zinc on the other side. So if we rewrite this once and fill in some of this, so we have Na solid, yields Na3, PO4, and so we'll fill in 3 zinc atoms on this side, or 3 moles of zinc, whichever way we want to interpret it. So the zinc is taken care of. How many units of phosphate do we have? We have 2 units of phosphate on this side. We have 1 unit of phosphate over here, so we need to put a 2 here. We have, as we're going through this now, all of a sudden 6 units of sodium, so we have to put 6 units of sodium on this side. So let's rewrite it once just to make sure it's clarified. So we have zinc phosphate plus 6 sodium yields 2 sodium phosphate plus 3 moles of zinc metal. And again, we have a balanced equation. So you can see that using these steps, you can balance all of these fairly straightforward. without too much difficulty, and hopefully you'll be able to make use of the process without too much difficulty in handling the reactions. Thank you.